Welcome students. In this lecture we will consider miscellaneous exercises as an application of definite integrals, and we will solve various problems and compute area of simple and complicated shapes. Let us consider the example that we have seen in the last class. Here it will be good if you assume A positive and M positive, so that we can plot both the curves given. So, if this is your x axis and this is your y axis, so y square equals to 4x is a parabola whose vertex is 0 0, and y equals to mx is line passes through origin. So, if A is positive, the parabola will be drawn like this, and y equals to mx, if m is positive, we can plot like this. The area bounded between them is this. Let us divide this area into elementary areas, thin vertical strips. So, if one such strip is having dx as width, so elementary area will be y from this minus y from this. So, we get under root 4ax minus mx under root 4ax minus mx, as this is our elementary area. So, required area is four under root 4ax minus mx dx, where we are supposed to put the values of x. So, value of x starts from origin and it goes to this point. To get the x coordinate of this point, we need to solve both the equations. So, if you put y equals to mx here, you get m square x square equals to 4ax. So, m square x minus 4a into x is 0. So, x is 4a by m square, x is 0. So, this gives you two, x equals to 0 gives you one point of intersection, that is origin, and the x equals to 4a by m square gives you another point of intersection, that is. So, this is your x equals to 4a by m square. So, limits of integration will be x equals to 0 to x equals to 4a by m square. So, your required area is 0 to 4a by m square under root 4ax minus mx dx. Now, you can integrate this. These are simple integrands where antiderivative is known to you. So, you get this 0 to 4a by m square minus m by 2 x square 0 to 4a by m square. you get 2 by 3 4a by m square under root 4a by m square minus m by 2 16a square by m to the power 4. So, we get 32 a square by 3 m cube minus 8 a square by 2 m cube, sorry, 8 a square by m cube. So, we get 8 a square by m cube, 8 a square by m cube is the final answer. Let us take another example. Compute area bounded between x axis y equals to 2 x cube minus x square minus 2x and x equals to minus 1 to x equals to 2. Now, it seems that it is difficult to plot this curve y equals to 2 twice of x cube minus x square minus 2x, but unless you plot you cannot find out the actual area, because if you try to integrate it directly, this will not give you a correct value of the required area, because you do not know where y is positive and negative between minus 1 and 2. So, this is not the right approach. So, you have to have some idea of the curve, that where it is positive and where it is negative. So, for that let us try to factor y equals to twice of x cube minus x square minus 2x. So, you can write this as which you can write as so you can see that x equals to 0, x equals to minus 1 and x equals to 2, this curve is crossing x axis. So, let us try to plot it roughly, so that we have some idea where this where is area is above x axis and where is this area is below x axis. Let us plot so that we can know where this area is above x axis and where this area is below x axis, since it vanishes at x equals to 0 and minus 1 and 2. So, let us draw these points minus 1, 0 and 2. So, at these points curve is taking 0 value, that means it is crossing x axis. Now, when x is between minus 1 and 0, x plus 1 will be positive, x will be negative and x minus 2 will be negative. So, y is positive. So, once x is less than 0 and greater than minus 1, this term is positive, this term is positive, this is negative, this is negative. So, total is positive. So, it will be like this. Similarly, if x is positive, so x plus 1 is positive, but x minus 2 will be negative when x is less than 2. So, y is negative when x is between 0 and 2. So, the curve will be something like this roughly. So, the total area required is now shaded by green color, you can see. So, we have to compute both and add them together to get the actual area. So, let me draw it again. So, it goes like this and this. Your this equation of the curve is twice of x cube minus x square minus 2x. So, 2x cube minus x square minus 2x. So, area, say this is A1, this is A2. So, let us compute A1. A1 is minus 1 to 0, 2x cube minus x square minus 2x. So, elementary area will, so this is A1, elementary area will be this into dx and integrate it. So, you get so you get 0 minus 1 by 4, then minus, okay, at 0 it will be 0. So, I have to put minus of, then so this value, so this is plus and then this will be 1 by 3 and then this will be minus 1. So, this is minus 2 by 7 and this is 7 by 12 minus 1. Sorry, minus 2, 7 by 12 minus 1. So, we get minus 2 minus 5 by 12. Okay, fine. So, we get 5 by 6, this is correct. So, then A2, this is equal to 0 to 2 twice of x cube minus x square minus 2x dx. This is equal to 2x to the power 4 by 4 minus x cube by 3 minus x square 0 to 2. At 0 it will be 0. So, value will that we will get is 2, 16 by 4 is 4 minus 8 by 3 minus 4. So, we get minus 16 by 3. So, total area is A1 plus mod A2. So, 5 by 6 plus 16 by 3, which is equal to 37 by 6. Let us take another example. Find out area bounded between y equals to 2 minus x square and y equals to minus x. So, at the very first step, for every problem on area, you have to have some idea about the region, where it lies, whether it is on positive side or whether it is negative side. So, plotting is must. So, this represents a parabola, inverted parabola, whose vertex is 0, 2 and axis is y axis. So, you will get this parabola. Now, y equals to minus x is a straight line with the gradient -1. So, you get this y equals to minus x, and this is y equals to 2 minus x square. So, area bounded between them will be this. So, again, so by the process similar to the previous cases, divide this area into thin vertical strips or rectangles, that is known as elementary area. So, this elementary area will be 2 minus x square minus of minus x into dx, fx minus gx into dx. You remember the formula where we have taken two curves fx gx such that fx dominates gx and the area bounded between them. Try to recall. So, we got fx minus gx into dx. So, fx is 2 minus x square, gx is minus x. So, we got this. This is your elementary area. Now, value of x for which the entire shaded area is drawn will be, one value is this is x minimum and this is x maximum. We need to find out both the values and then we will put it here, x minimum, x maximum. So, to find out these x minimum and x maximum values, we need to solve equation of both the curves. Minus x is equal to 2 minus x square. So, we get x square minus x minus 2 equals to 0. So, values of x will be that will give you 2 comma minus 1. So, this x minimum is minus 1 and this is 2. So, this entire shaded area lies between x equals to minus 1 and x equals to plus 2. So, we need to put the limits over here and we get 2 minus x square plus x dx integrated, we get 2x minus x cube by 3 plus x square by 2 minus 1 to 2. So, we get upper limit, value of the antiderivative at upper limit is 4 plus 2 minus 2 minus plus 1 by 3 plus 1 by 2. So, this is equal to, so this 4, this and this is 8 minus 8 by 3 minus 5 by 6, this is 8 . So, this is your final answer. We are solving miscellaneous problems so that you are able to plot a curve, then identify the region and then you should be able to put the limits properly. So, let us take another example in the sequence. Area bounded between y equals to x 4 minus x square x axis and x equals to minus 2 and x equals to plus 2. So, at the very first instance it seems that since the area is bounded between minus 2 and 2, so if you integrate x 4 minus x square dx from minus 2 and 2, you will get the value of the integral. But what will happen if you do that without plotting? If you try to approach and plot and integrate this function from minus 2 to 2, so this is an odd function, so immediately the value will be 0. So therefore there is some problem with our approach. So without plotting we cannot proceed, so we should have some idea, rough idea of the curve. So let us draw it first. So what you can see is that y is 0 when x is 0 and y is 0 when x is plus minus 2. Now between 0 and 2 y is positive, and between minus 2 and 0 y is negative. So it vanishes at 0, 2 and minus 2. The curve vanishes here, 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 and from minus 2 to 0 it is negative, and from 0 to 2 it is positive. So we can have this kind of shape because it is continuous also. To find out how this curve will look like here and here exactly, if you are interested in knowing more about the curve, you have to find out the derivative and find out the value of the derivative at 0, minus 2 and plus 2, so that you know how the curve is crossing at minus 2, 0 and 2. So actual area that we are looking for is that is lying between the curve x axis and lines x equals to minus 2 and x equals to plus 2 is this. So total area required will be, say this is A1 and this is A2. So total area required is mod of A1 plus A2. So we will compute A2 first. So A2 will be given by 0 to 2 x under root 4 minus x square dx. Since this curve is symmetric and an odd function of x, this A1 will be having same magnitude as that of A2 but negative sign will be there. So A1 will be minus of A2 and A2 is 0 to 2 x under root 4 minus x square dx. Now assume that x square is t, so 2x dx is dt. So 0 x0 is t equals to 0 and x2 is t is 4. So limits will be this, and x dx is 1 by 2 dt. So you get 1 by 2 4 minus t dt, 1 by 2, integration will be 0 to 4, 4 by 3. At 4 it will be 0, and at 0 it will be 0 minus minus sign will appear as you have minus t here. So, at 4 it will be 0, and then at 0 it will be 4 to the power 3 by 2 minus sign. So, you get minus plus 4 by 3 into 8, that is, sorry, we have one mistake here, we get 1 by 3. So, we get 1 by 3. So, finally, we get 8 by 3. So, A2 is 8 by 3, A1 will be minus 8 by 3 because function is odd. So, total area required is 16 by 3. Let us take another example. Area bounded between two parabolas, y equals to x square and y equals to 8 minus x square. So, let us plot them. Y axis, x axis. Y equals to x square is parabola vertex 0 0, and axis is y axis. We get this, and y equals to 8 minus x square is parabola which is inverted at whose vertex is 0 comma 8. So, we will get this shape. So, we need to find out these two point of intersection, and the required area is shaded by green color. So, again we divide the area into elementary areas, thin strips or rectangles. If one such strip is having width dx, so elementary area will be 8 minus x square minus x square dx. We need to find out these two values. So, for that we need to solve both the equations. So, this is minus 2 0 and this is 2 comma 0. So, limit of x will be from minus 2 to 2 and minus 2 to 2, 8 minus 2x square dx. Since this is, if you replace x by minus x, you can see that the sign of this integrand will not change, and f of minus x is equal to f x. Therefore, it is an even function. So, you can use the property of the definite integral that minus a to a f x dx is twice of 0 to a fx dx. So therefore we can write this as 2 0 to 2 8 minus 2x square dx. This is equal to 2 8x minus 2 by 3 x cube 0 to 2. So we get this value of the required area is 2 16 minus 64 by 3. Let us take another example. Find out area between y equals to 1 minus cos x to sin x, x axis x equals to 0 and x equals to pi. So this seems very complicated curve and it will not be easy to plot it, but you should know whether it is positive or negative and you should have some rough idea about the curve. So if this is x axis, this is y axis. So between 0 and pi, what is the nature of the curve 1 minus cos x into sin x? So if say this is 0, this is pi. So at x equals to 0, y is 0 because of both the factors. X equals to pi also, y is 0 because sin pi is 0. Now between 0 and pi, is there any chance of vanishing the function again, or is there any chance that y takes negative value? Since cos x lies between minus 1 and 1, sin x is as always positive or 0 between 0 and pi, and 1 minus cos x is always between 0 and pi. Therefore this curve is always positive. So you will have this kind of shape of the curve. So your required area is this, and if dx is width of elementary area, then elementary area will be 1 minus cos x sin x into dx, and this is your elementary area, and total area will be 0 to pi 1 minus cos x into sin x dx. Let us evaluate it. 0 to pi sin x minus sin x cos x dx, which you can write as 0 to pi sin x 1 by 2 sin 2x dx, which is minus cos x plus cos 2x by 4 0 to pi. So this will give you minus 1, and then at 2 pi and 0 you will get 1 minus 1, so plus 1 by 4 1 minus 1, so finally you get a 2. This problem is very simple, but you should remember that unless you have some idea about the curve, whether it is on either side of x axis or it is changing its sign, you cannot find out the correct area. Let us take another example. Area bounded between y equals to cos square x and y equals to 1, x equals to 0 and x equals to pi. So, how to plot this region? You know how the graph of cos x looks like between 0 and pi. So, at 0 it is 1, then at pi by 2 it is 0, and then again it is pi, at pi it is, so this is plus 1, this is minus 1. This is the graph of cos x. Now, if you square it, how the graph of cos x will look like? So, this portion will go up because you are squaring it. So, this is rough sketch of cos square x. So, and because the values lie between minus 1 and 1, so it will not cross 1 between 0 and pi. So, it will, and pi by 2 it will be 0, so it will be something like this. So, your area that you are looking for, that lies between the curve y equals to 1, this is your cos square x, this is your y equals to 1. So, required area is shaded by green color, and this is your required area. Now why this is smooth here? So, that is very easy to find, that why this cos square x will be smooth at pi by 2. So, you need to just find out the derivative, and you can see that y dash will be 2 cos x into minus sin x, and that will be 0 at pi by 2. So, therefore, the curve is smooth. The tangent at pi by 2 is x axis. So, required area is therefore 0 to pi. Elementary area will be the vertical strips. If we take length dx, then we need to apply again that theory where we have two functions f(x) and gx, and the area lies between a and b. So, you write f(x), you write this a to b f(x) minus gx dx. So, f(x) is 1 and gx is cos square x. So, you get this is equal to 0 to pi sin square x dx, which is 1 minus cos 2x by 2, 0 to pi dx. Area therefore is equal to 1 by 2 x minus 4, 0 to pi. So, you get pi by 2 minus 0 minus 0. So, this is pi by 2. So, till now we have solved lot of examples on applications of definite integrals. Let us see, there are certain properties which we have not covered till now, and let us discuss them in brief. So, let us see what can be done in this regard. A definite integral is written in this form, where we have taken f(x) to be continuous on closed interval a b, and our both endpoints of the interval are finite. So, whatever problems we have solved, f(x) was a continuous function, and both a and b are finite. So there are two questions that can be raised. What if fx is discontinuous on AB, and another question is what if interval of integration is not bounded, that is your interval is a to infinity, minus infinity to a, or minus infinity to infinity. Let us see how to deal with such situations. For that, let us take the case where fx is discontinuous on the interval AB, but fx is piecewise continuous So to understand this, let us take integral minus 2 to 2 where this is known as greatest integer function, and the plot of this can be done as follows. So greatest integer function is defined like that. Between 0 and 1 it takes value 0, at 1 it takes value 1, and between 1 and 2, just before 2, it takes value 1 throughout. This is 1, and between minus 1 and 0 it takes minus 1. At minus 1 it is minus 1, and between minus 1 and 2 it is minus 2. Sorry, not this, but somewhere here. This is minus 1, this is minus 2. So if you want to integrate this in this interval, you can write this integral as equal to minus 1 to minus 2 to minus 1, where the function value is minus 2, plus from minus 1 to 0 function value is minus 1, plus 0 to 1 function value is 0, plus 1 to 2 function value is 1 dx. If you integrate this, you get minus 2 x minus 2 to minus 1 plus minus 1, integral is x minus 1 to 0 plus 0 plus 1 to 2, x 1 to 2. So value is plus 2 minus 1. We are applying the formula of definite integral, fundamental theorem of calculus 2. So we get minus 2, here we get minus 1 and then 1. So value is minus 2. So, now let us try to understand. So, the function is not continuous throughout, but between minus 2 and minus 1 it is continuous, between minus 1 and 0 it is continuous, from 0 to 1 it is continuous, and from 1 to 2 it is continuous. So, you can break the integral in you can break the integral over those subintervals, and you can then evaluate it on individual intervals. Now, if I ask you to find out area under the given curve from minus 2 to 2, so area will be represented by this, this and this. Then we have to take, so area of this was minus 2, area of this will be mod of minus 2, that is 2, and area of this will be mod of minus 1, that is 1, and here it is 1. So, if I ask you to find out area, then you have to put mod over here, because this is giving you negative values since the curve is lying below x axis. So, you have to put mod and then add it together to get the value of the area. So, we have seen how to evaluate a piecewise continuous function. Now, let us observe what will happen if your interval is not bounded, or it contains plus infinity or minus infinity. So, there are several cases in that. So, let f(x) be continuous, but interval of integration is not bounded. So, the first category is, say for example, so you can see that this function is continuous everywhere, but the interval of integration is infinite from 0 to infinity. Then another case is from minus to infinity 1 by 1 plus x square dx. Then another case where function is discontinuous, but interval is finite, say a to b, where a and b both are finite. Here discontinuity does not mean piecewise discontinuity or piecewise continuity. So, this discontinuous function means it has infinite values somewhere in the interval of integration. So, for example, (0 to 1) dx by root x. If you see the graph of 1 by root x, it tends to infinity when x tends to 0, and it tends to 0 when x tends to infinity. So, this is the graph of 1 by root x. This is y axis, this is x axis. So, I want to compute the area, this area. Then third case is where the function is also discontinuous and interval is also not finite. So, case 3 where function is discontinuous, which are not continuous, also interval of integration is infinite. for example, minus infinity to infinity 1 by x square dx. So, here 1 by x square is not continuous at x equals to 0, and interval of integration is also unbounded or infinite. So, let us solve some examples and see how will you deal with such cases. So, example 1, 0 to infinity 1 by 1 plus x square dx. So, if you plot this curve, at 0 it is 1 and at infinity it is 0, it will go like this. So, this is the area that is governed by this integral. So, if you see, you cannot apply limit of finite sums, because this you have to add infinitely many areas of elementary rectangles, and so the theory that has been developed so far is for finite interval. So, what we do, there is a very simple trick. What we do, we just write 0 to a 1 by 1 plus x square dx, and then since now a is finite, so we have taken say some value here a, and then we are integrating this area. Finally, we take limit of a tends to infinity, and then the final value of the integral is computed, and theory for this is well developed. So, if the interval is finite and this function is continuous, then by fundamental theorem of calculus 2, we can write the value of the integral as, so tan inverse x is the antiderivative. So, we get tan inverse infinity, that is pi by 2. So, what we have done, this infinity is dealt by converting this integral into limit of this integral, which is defined over finite interval. Hence, the problem of unbounded intervals can be dealt in this manner. Take one more example, 0 to 1 dx over root x. If you plot this curve, you get x0 1 by root x tends to infinity, this is y axis, this is x axis. So, you want to compute, this is 1, so this is x equals to 0, this is x equals to 1. So, you want to compute this area. So, you can see that since if you draw it in very small rectangles, you can see that when you move towards 0, you will not be able to write the area of the rectangles, because function value tends to infinity. So, what we do, the idea is same. Again, we assume that, okay, say this is epsilon comma 0, and then we evaluate this area, and then we take limit of epsilon as epsilon tends to 0. So, for that we need to write this integral as epsilon to 1 dx over root x, x epsilon tends to 0. So, this is equal to limit epsilon tends to 0. Now, 1 by root x is continuous in epsilon to 1, closed interval epsilon to 1. So, you can apply fundamental theorem of calculus, and then you can write the value from silent to 1, which gives you two minus 2 epsilon. So the value of the integral is 2 under root x. So you get 2 minus 2 root epsilon, and after the taking the limit, you see that the value of the integral is 2. Such integrals are known as improper integrals. Such integrals you can deal with by defining the integral as a limit of integral over finite interval. We have seen certain miscellaneous examples on definite integrals, on area, and definite other kind of definite integrals. So in our next class we shall continue with miscellaneous examples and see how to approach such complicated problems. Thank you.